Let us continue from where we left last time. So the game plan for today would be we would uh, discuss some of the basic ideas from the theory of stochastic processes that are of relevance to optical coherence, the study of optical coherence. Because to understand coherence, we have to borrow tools from stochastic processes and probability theory. So of course, we will not be looking into the formal mathematical aspects of stochastic processes, but only look at the ideas and try to understand them conceptually and see how we can borrow those tools to appreciate optical coherence better. So once we do that one today, next time we meet, we will try to discuss the concept of analytic signal as why that concept is relevant in the study of optical coherence, and then see how the ideas from stochastic processes that we discussed today, how are they incorporated to understand temporal and spatial coherence. So once we do these two things, then we will be able to do a full-fledged calculations in an interferometric setting to understand temporal and spatial coherence in terms of correlation functions. Okay, so once this module is over, then we will make a transition to quantum optics and try to see how all these ideas carry over in the quantum landscape. Okay, and try to understand the concept of correlations in quantum optics, and we will then discuss various quantum states of light. Okay, so we last time we discussed that when fields coming from two different space-time points are perfectly coherent, then the interference is perfect. Okay, now if the interference is not perfect, it only means that the fields are not highly coherent, they are only partially coherent. So which means the quality of interference, by which the visibility pattern or the quality of interference fringes tell us how good, so how strongly or poorly the field is correlated. Okay, so means so high visibility means the moderate visibility means partial coherence. So highly coherent sources, perfect will be the visibility, but most of the sources in real world are partially coherent. Okay, that's why the visibility will be moderate. Of course, if the source is completely incoherent, then such an optical field cannot interfere, so there won't be any visibility. Okay, of course, no visibility doesn't mean that everything will be pitch dark. It just means that you will not see the contrast on the screen. Okay, it will just be a smooth or a fuzzy distribution of light. Okay, okay, so what is the source of randomness in the optical field? Of course, as we discussed last time, the fields produced by a real source are more or less random because a source has several atoms. So an atom or emitters, whatever we want to call it, and each atom emits at random. Okay, there is no correlation between the emissions of different atoms. So each emission process is statistically independent with each other. Okay, and that is a source of randomness in the optical field. But however, in order to observe interference, we need some kind of order. Okay, we need some kind of a correlation in the field. So one intuitive way to define coherence is the degree of order in a random field. We know that the field has random fluctuations, but can we try to find some kind of order? Okay. Can we, and not just find some kind of order, can we come up with some measure to quantify this order so that we know how good, how strongly or poorly correlated the field is, or how good is the quality of coherence? Okay. Now, the branch of optics that deals with these kinds of questions is called statistical optics. So statistical optics is the study of the properties of random light. Of course, the randomness in an optical field can be due to various factors. One is due to the nature of emission in the source, but that's not the only source of randomness. You can also have randomness due to scattering. Say the scattering of light in a turbulent medium, in a disordered medium, that can also induce randomness, random variations in the optical field. But right now, we won't be concerned about the source of randomness. Okay. As far as our investigation of optical coherence is concerned, we will assume that the optical field has some random fluctuations. Given this, can we come up with some kind of measures to understand optical coherence? Are the conditions under which one can observe interference? So the study of random fluctuations of light is formally known as the theory of optical coherence. Okay. So this is what it is. So can I clean this part of the board? So let us consider this. This is a perfectly harmonic wave. It's monochromatic because it has a unique frequency. So the dependence of the wave function on time and position is perfectly predictable and deterministic in this case. Okay. So there is no notion of randomness, this one. So to discuss such a wave function or such an optical wave, we don't need to borrow any ideas from statistical optics. Okay. However, for a random light, the moment you induce fluctuations in the field, this goes away. Then no longer will the position and the dependence of wave function on time and position will be perfectly deterministic and predictable. So now the question is, you will have some kind of a signal will have random fluctuations. Okay. Now the question is, given this scenario, given the fact that your signal has all these random fluctuations, can we come up with some kind of meaningful measures to characterize these fluctuations in terms of some statistical averages and still see some kind of an order? Because coherence is the degree of order in a random field. Given a random field, can we come up with some kind of measures, meaningful measures, predictable measures? I mean not predictable, verifiable measures. When I say verifiable, I mean experimentally verifiable measures that would characterize the randomness and still discuss the concept of coherence. Okay, that's what we'll be doing next. So this randomness is also inherent to classical fields simply because of the source. So you have, so you can take any source, let us take an incandescent bulb, any source. A source has millions of atoms. So whatever light that we see from a source is due to the emission from all the atoms, right? And each atom emits independently. And there is no, in general, there is no statistical dependence between the emission processes of different atoms. So which means the field that each atom emits doesn't have to be correlated in either phase or time with the field produced by its companion, by its neighboring atom. So which means, and the total field that you observe from a source is the sum total, is a superposition of all these fields. So which means because the emission processes are statistically independent, that inherently gives rise to fluctuation.
Does that mean that this emission process is inherently quantum, unpredictable?
No, so quantum, the notion of the notion of probability or uncertainty is even much deeper. Right. So in quantum, it is not just due to the emission process alone. Even you can have coherence due to part indistinguishability. So something even more fundamental. But right now, this is purely classical. So whatever we are discussing right now, it's within the realm of classical optics. It is random because of the nature of the emission process, which means, in principle, if one could come up with tools to individually investigate the emission process of each atom, which means we should be able to remove this randomness. But that is not the case in quantum mechanics. The notion of uncertainty is much deeper in quantum optics. So here, this randomness is simply because you have millions of atoms and they emit independently of each other.
In principle, one can try to design some filtering process to which you can, identify one signal from one set of one atom, and the remaining you can throw away.
Yes. So yes, that is true. So if that is true, so if we can come up with a filter where you choose only a specific bandwidth, then which means you just put that filter in front of the source, which means then you will throw away anything that falls outside that window. But still, within that window, there is going to be some fluctuation and randomness that we cannot overcome. Yeah, yes, you can.
So if we're looking at classically, all the atoms have a well-defined frequency which they emit, right? Classically, there is no uncertainty, so it is on the dot omega. It's
there is always you will have a spread, because the thing is, if you have, because if you have a finite coherence time, then the bandwidth will have to be finite. Because if what it means is, if all the atoms were to emit on dot, which means if the emission is strictly monochromatic, that it's at this lambda 810 and there is no deviation whatsoever, that would mean that the coherence time should be infinitely the coherence time should be infinite.
That because it does not emit at 810, that is because the energy level has a finite spread.
Yeah. So it is
a quantum.
You mean the atomic emission process is inherently quantum? So true. That is true.
Suppose atoms could emit on the dot, all of the atoms, if it is possible. Then
no, but the question is, they don't emit on dot, because because it's like you have the energy level is like you have a distribution.
Yes,
and it's just that you know the probability of emission from each energy level, and the one that has the highest probability is taken as the energy level. That's the frequency of transition, and then the rest becomes your detuning, or what you call that line width, the spread.
Then the fluctuations will be inherent in
No,
quantum.
true. Fluctuations are inherent in quantum too. I'm not saying so. What I'm saying, in quantum, the notion of uncertainty
That is
That's
different,
what.
that path also comes.
Yeah, true.
Let's say we take a bright light so that path, etc., does not come into.
Sure.
Then also the fluctuations that will be present, that will still be due to the quantum nature of these, due to the spread due to quantum nature of this energy level, right? If say these were totally precise, what else could be the source of fluctuation classically?
You mean if these emission processes?
If these emission processes were, let's say they don't have alignment, like they on the rod.
Oh, you mean hypothetically speaking, if you can make them.
You can,
if you can make them precise, then of course then you should be able to eliminate the random fluctuations. If hypothetically speaking you make the emission precise, strictly monochromatic, and if the atoms emit coherently, okay, the emission processes are not statistically independent. What I mean is they emit at the same time and they preserve the phase relationship when they emit. Then of course you will be able to in principle remove the randomness. Just like you write it as a perfectly harmonic way, but that's not what happens.
Classically only fluctuation is this randomness due to statistical independence.
Yes, at the source.
Phase will be
the randomness from the source is due to the statistical independence of the emission process. Of course, you can also have random variations when you let the field propagate due to scattering. Scattering can induce randomness too, but we are ignoring propagation right now. So right now, in the context in which we are discussing, the randomness is due to the source. It arises from the source.
If randomness exists, so can we write it mathematically similar to this?
Yeah, that's what we are. Yeah. So you mean the moment because of the randomness, whatever meaningful quantities that you would want to calculate will be in terms of statistical averages.
Not like function.
No. Everything. So the intensity of light will be expressed in terms of expectation values. So you won't be able to write down a wave function like this. So that's what statistical optics is all about. So we will whatever meaningful quantities we calculate will be in terms of averages. True, very true. Yes. So yes, it's true that the physical motivation came from experiments, and then we are on top of that we are borrowing tools from the theory of probability and stochastic processes to construct a framework. And of course, our motivation will be mostly phenomenological. So where we try to okay. So yeah. So any other question? Oh, you wanted to say anything, Professor Ghosh?
No.
Okay, so
we are not asking about the origin of fluctuation. We are just looking at it phenomenologically.
Yes.
If I have the fluctuation, then what we can do?
Exactly. So yes, given the fact that you cannot get rid of fluctuations, given the fact that you cannot, you don't have the phase is not predictable and deterministic. So the question is, what can be done? Can we still come up with some?
Yes, I think the source is considered to be classical.
Yes.
The source field is considered to be classical.
That is true.
Otherwise, you will have to modify everything.
That is true. The source is classical.
The source field has to be classical in nature. So you cannot consider all the quantum properties like uncertainty.
So this has a precise energy.
It has the energy gap, but the fluctuation, randomness is there in the field.
That is due to sources.
Yeah, that is due to sources. And you don't consider any quantum nature of that randomness. Because these kind of light we get to see, like, this light is perfectly random light.
That is true. Yes.
Exactly.
So yes, so here we don't take into account the quantum mechanics of the emission process. We just have a source which has a collection of emitters and they emit. Of course, we do appreciate the fact that the emission is when the atom from an excited state goes to a ground state. That's about it. Beyond that, we don't take into account the quantum mechanics of emission. That's it. So why is it that, why do we need statistical optics? So let us say we have a waveform like this, and say if another experiment gives waveform such as this, let me call this A, let me call this B. By a mere visual observation, all one can say is, of course, B seems to be more intense than A, or B fluctuates relatively more rapidly than A. But beyond this, we can't do much. So the question is, what kind of statistical averages that we need to calculate in order to figure out whether the optical source is coherent, highly coherent, incoherent, or partially coherent. So our ultimate goal is to relate all these averages to those three terms: incoherence, coherence, or partial coherence, because that's all we care about, because it's the nature of coherence that's going to really tell us how well the fields will interfere. Okay? So which means whatever average mathematical quantities, statistical quantities that we calculate will be related to characterizing coherence. So which means we won't be calculating all the quantities that one can in principle calculate using the theory of stochastic processes. So we'll only be interested in those quantities that are related to optical coherence. So let us consider some random process x of t, and let us consider the kth realization, because by the moment we talk about random process, it just means that we have an ensemble of realizations. So let us just consider the kth realization. So we can define what is known as a time average. So the time average so this is the time average. Of course, once we have defined this one, we can also define time average for any deterministic function of this random variable x. So which what I mean is, let us say your f is x square or sin x, then formally you can define the time average of that quantity by x k square of t dt integrated over from minus t to t divided over 2t, or you have sin x. If that is your realization, then sin xk of t and carry out this process. So that's what it is. So once we have this definition of time average, in principle we can calculate a time average of any deterministic function. Okay. So which means when I say deterministic function, what we mean is we are not going to induce any other randomness. Okay. The randomness is only in this x of t. Yeah. And there is another kind of average that we can define, which is called the ensemble average or the expectation value. And so that is intuitively defined as This is how we intuitively define. And then what we do is we formally let n go to infinity, because then we assume that there are infinitely many realizations. Now, this is called of course, when we actually solve problems, we try to define it even better, where we define a probability density function. And in terms of the probability density function, we define the expectation values. So in that sense, it's the expectation value. This can be defined even more formally. So this is the probability density function. So what does this probability density function tell us? It just tells us, it represents the probability that the random field variable x will take a value in the range x to x plus dx at time t. That's all it tells us. Okay. So once we know determine what the probability density function associated with the random process is, this is straightforward in principle. Maybe integration can be hard, but in principle it's straightforward. We know how to calculate the ensemble average. Of course, once we know this one, we can also, once again, similar to this one, we can calculate the expectation value of any deterministic function of x square, sine x, whatever, which is straightforward. But the question is, of course, one more thing is, we don't have to stop with just x. We can calculate any higher order moment, formally speaking. So this is called the kth moment. And the first moment by definition is the mean. When k equals 1, you get this one. That's the first moment. Sometimes it's also convenient to define what are called central moments, basically moments defined around the mean. So the kth central moment is defined as and you can always see that the first central moment is 0, because you put k equals 1, this gives us, this is going to give you average x, and this already this you have an average x and a minus sign, it goes away. So k equals 1, and the second central moment gives the variance. Of course, if the random process is Gaussian, so we know one of the unique properties of Gaussian processes or of a Gaussian, that we can be done with everything by just calculating the first and the second moment. We don't need to calculate the higher order moments, but that is true only for a Gaussian. In general, This is not the case for a general probability density.
If you take any probability density other than Gaussian, then all its higher order moments will be non-zero.
Oh, but is that a theorem? Is that a theorem like other? Oh, okay. So that's a formal mathematical.
Yes. So it's called get the name. Anyway, so it says that if I take a probability distribution,
Uh-huh.
Gaussian will be the first order and second order moments,
Yes.
which will determine all the other higher order moments. But if you take a non-Gaussian probability distribution, this is not in terms of moments, but this is this kurtosis, what are they called? The
Kurtosis skewness, that K
skewness,
equal to
yes,
K4.
skewness, yeah. So there it has to be non-zero for every higher value.
Okay. Oh. So okay. So these are some basic definitions and formulas involving statistical averages. But this by itself will not be sufficient for us to investigate optical coherence of a random field, a random signal. The reason being, we can't just consider only the probability density at a single instant of time to investigate optical coherence. Why? Because what we need to understand is how are the fields correlated at different instants of time and at different locations in space. So which means a single variable probability density alone will not be sufficient. So which means we need to consider multivariate like probability densities that involve different instants of time and different spatial coordinates. Particularly if you want to calculate quantities, say what is the average of such as this. Okay, you have a random process x, and if you want to see the statistical average at different instants of time.
Like what average is ensemble or time?
Ensemble average. So right now, so from now onwards, we will just discuss ensemble averages. Okay, and later we will invoke the concept of ergodicity. We'll assume that some of the processes are ergodic, where the time average is equal to the ensemble average. But right now, for the rest of the discussion, we will just consider ensemble averages. So to calculate this quantity, this will not be sufficient because this probability density only has one time variable. So it can only tell us what the field is at a given instant. But if you have two instants of time, so which means we need to sum up with so this will represent the probability that x1 takes the value x1 lies in the range x1 and x1 plus dx at time t1 and x2 in the range x2 plus dx2 at time t2, okay, and so on. So we can similarly formally introduce multivariate probability densities phi of x1 x2 until x1 t1 t2 until tn, but mostly we'll be interested in this one because typically in any optics experiment you either do singles detecting a single optical field or you do a coincidence. So either at the same instant or within a time interval you try to detect two optical fields simultaneously. So typically we will be either using this one or this one, even though formally you can always define probability density functions involving several spatial variables and several time variables. Pretty much this will do the work for us. Okay, so having defined this, so formally so this is how we define this average. Okay. So you define this joint probability density and then play the same game that we played earlier. It follows. Now now the question is, when we do an analysis, should all the random signal, the random process that we consider, should they necessarily be real? Because so far we just assume that all of them are real random functions. We can also extend these ideas and generalize them to complex random fields. So let us say you define a random field, Z of t, then you can always formally define probability densities such as and then what we do is so let us say you want to so basically this is nothing but dx dy because this is your complex plane
Like then Z to be like then Z to be an analytic function.
yeah sure, you could formally play this game. So what I'm saying is your probability densities or the random signals don't have to be real mathematically. You can play this game with complex signals too. Okay, and next time we will introduce the notion of complex analytic signal but please note that the optical field, the physical field is always a real quantity. So the physical field is not a complex quantity. We use ideas from complex analysis for mathematical convenience, not unlike quantum mechanics where the quantities are complex inherently. In classical optics, the optical fields are real quantities. So if you say that, okay, I don't want complex analysis, I don't like complex analysis, you can live your life by just using real quantities and playing with them. But this is more out of convenience, not out of necessity. Of course, so however, if you want to define the correlation at two different instants of time with a complex optical field, then the way we define it is one is conjugated this is how we define the correlation or the statistical average between I mean the average of a complex signal, optical signal at different instants of time at t1 and t2. So it's z1 conjugate, you conjugate one of them, and then z1 conjugate z2. And this should also give us a hint as why in quantum optics the averages are always E plus E minus or A dagger A. You take the Hermitian conjugate of the first one times its adjoint. Okay, So this is how we define the statistical averages in terms of complex quantities. Okay, so now let us define some more relevant quantities which we need to understand to appreciate optical coherence. That one is autocorrelation. So we just use this. We'll use the letter R because that's a standard symbol in the literature. But when we actually start discussing optical coherence and start calculating correlation functions, we will switch to the symbol G. I think that's what G is what is being used in classical and quantum optics. But right now, for the formal definition, we'll stick to the symbol used in the literature, which is R. And so this is the autocorrelation function. Of course, if you want, we can also define another quantity which is called autocovariance, which is denoted by this letter C. So basically, this is defined in terms of the central moment. This is called autocovariance. But mostly we'll be concerned only with autocorrelation. But we are just introducing this for the sake of completeness. So formally, what it means is so we can formally expand this product. And if you do that, what you would get is basically it's the autocorrelation minus the product of the mean at T1 and T2. So all you have to do is just expand this one. So the first one is x1, x2 times this one. That by definition is your autocorrelation. Okay, and then x1 times mu of T2. This is a constant. So pull this out of the integral, and x1 times this one just gives you mu of T1. Okay, likewise mu of T1 times x2 times the probability, which gives you mu of T2. And the last one is just 1 because mu of T1 and mu of T2 are constants. This is normalized to unity. Okay, that's how you get this one. Okay, this is the relationship between autocorrelation and autocovariance. Yeah.
That is also autocorrelation.
Which one?
Z1.
Yeah, certain. Yeah. In terms of this complex signal, yes, absolutely. Okay, so this is in terms of this is how we define autocorrelation. But now we need a generalization of the autocorrelation function for situations involving two different random processes, x of say x and y. Okay, so far we've only concerned ourselves with a single random process, but we investigated it at different instants of time and tried to define various kinds of statistical averages. But what if we have two random processes? So you have two optical fields, independent optical fields. Now Now, can we still investigate some kind of correlations between them? Can we come up with some kind of meaningful statistical average to quantify the correlation between two different random processes? Yes, and that is called cross correlation. So I'm just using a subscript here, x and y, to denote that we are talking about cross correlation between two different random processes. Now, this is how we define cross correlation. This is a definition of cross correlation. Once again, analogous to autocovariance, we can define cross covariance this is what it is. And this is how the cross covariance is related to the cross correlation function, very similar to what we saw here. So one thing is, it's not as if the cross covariance conveys any additional information that you don't have in the cross correlation function, just as the autocovariance does not convey any additional information. It is just a matter of choice. If you want to work in terms of central moments, you resort to autocovariance. But if you just want to calculate the correlation and you're fine with that, it's more than sufficient. We don't have to necessarily use this quantity. So we can do everything from autocorrelation. In fact, we will see that in optics, we just deal with the autocorrelation and the cross correlation functions. So we have just defined the cross covariance and autocovariance for the sake of completeness. But yeah, in principle, you can define these quantities too. So of course, in this case, in terms of cross correlation, if x and y are independent random processes, then we know that this is true. The joint probability density will be separable. We can write that as a product of the probability density of x at t1 times the probability density of y at t2. Okay. Second, two random processes x and y are uncorrelated if the cross covariance vanishes. Okay. So which means the cross correlation function will simply be the product of the mean at T1 and T2. So any question? So far we have just defined a bunch of quantities that we'll find them useful to understand optical coherence. So any question? So can I clean this part of the board? Yeah. So let us just work out a very simple example, just to get a flavor for the autocorrelation function. Let us say that we have a random process x of t, okay, which is given by this expression where a is a uniformly distributed random variable. Phi is not random. A is the only random variable here. Okay, and let us say that it has a mean mu sub a and variance sigma a squared. Okay, it's given to us. So what it means is, so you have all these realizations. So let us call this a minus a. This is the origin. So each one of them is a realization of the random process x. Okay, and this is phi. You can just fix phi. That's not a random variable. So the question is, what is the mean? This is not random. So this is the only thing that is random. But we know what average of a is. That's given to us. That's mu sub a. Right. So now what is the variance of a? So the variance of a is basically but this is given to us. Right. So this is the variance of a. So finally, how do we calculate the autocorrelation for this random process? Right. This is what it is. And we know what a square is because this is sigma a square. So basically, this is nothing but so Of course, if you wish, you could simplify this even more and write this as the sum and difference of cos. If you want to. So just a simple drill on how autocorrelation functions are calculated. Okay. So this is something that in the real world, we will have to use the experimental data or intuition to model the system by an appropriate random process. Okay. So this is something that we'll have to figure out. The most challenging part is this one. How do you come up with, how do you define your random field? Okay. Once that is done, the rest is straightforward. The rest is just mathematical drudgery. The calculation can be complicated depending on the actual problem on hand. But in principle, the prescription is given to us. The challenge is always this one. How do we use our intuition and the available experimental data to model a given system by an appropriate random process? Okay, so now next we will introduce the concept of a stationary random process. So far, in general, the statistical averages, the means, the variances will depend on time in general. Yes, please.
In this, we considered randomness only in the amplitude, not in phase.
No, not in this example, no.
Okay.
No.
But in real source, randomness will be there in both the amplitude and phase.
Yeah, you can have, yes. The phase can also be random. It can be.
Okay.
You can still assume that, say, the phase is uniformly distributed and treat it as a random variable and try to work out the problem. But in this example, only the amplitude is a random variable. A is random.
Okay.
So a stationary random process is one whose properties or statistics in particular do not depend on the origin of time. So which means if this is a joint probability density of n random variables x1 through xn at different instants of time from t1 to tn, then you displace time by a fixed amount tau. There won't be any change in the probability density, which means as a consequence, the statistical averages will also depend only on tau. It will not depend on the absolute values of T1 and T2. So this is in general. So for stationary, we just stop with this one. So this is a definition of a stationary random process where the probability density doesn't depend on the origin of time. So you just determine the probability density at some instance T1 through Tn. You displace each time by tau. The density remains invariant under this time translation.
No, my point is it's like, let's say I change by, let's say, tau prime. Then
you mean
with it, other than tau, I do it by tau prime. Then it should be also with us.
Yeah. So yes, but you displace each instant by the same time. Any value of tau. Any value of tau. For any value of tau. So it's not that, okay, I don't use,
Time translation invariance.
it's time translation invariance. So I don't do T1 plus tau 1, T2 plus tau 2, or Tn plus tau 1. I just displace time by the same amount, but it holds good for any value of tau. Okay. So this is a stationary random process. Now, a random process is called first order stationary. If so, in this case, this will be independent of time. Why? Because your t can be anything. So you can also, so if you take t equals 0, then the probability density at t equals 0 should be same as t plus tau. So which means for a first order stationary random process, your probability density doesn't depend on time. So which means the mean will be independent of time, the moments will be independent of time. As a consequence of this one, this is called first order stationary. Now, a random process is second order stationary if so in this case, the joint probability density doesn't depend on the absolute values of T1 and T2, but only on the difference. Okay. No matter what T1 and T2 are, as long as you keep the difference fixed, it is that value tau that's going to influence your joint probability density. So this is called the second order stationary process. Is also called Whiteson stationary or weakly stationary. This is often abbreviated as WSS. It's called weakly stationary with respect to the first order stationary process. Why? Because here the probability density doesn't have any kind of time dependence whatsoever. However, here it does depend on time. It's not as if in this case it's independent of time, but doesn't depend on the absolute times T1 and T2. It only depends on a difference. As long as you fix T2 minus T1, then it is that difference that's going to determine the probability density. At least that's the only parameter that will influence the probability density. So that's why it's called weakly stationary or Whiteson stationary. What's it? Yeah. So right now, yes. So in optics, typically we will always be concerned with, we do either singles or a coincidence detection. So which means we just compare the correlations at two different space-time points. So we pretty much confine ourselves to a joint probability density that depends on x1, x2. But in principle, you can define higher order probability densities. You can formally define higher order correlation functions. But all the experiments, most of the experiments perform to this day involve either detecting a single optical field or a coincidence. Okay, so it's going to be, so we'll just quickly write down the properties of some significant properties of autocorrelation functions, and then stop there because we have a seminar at 3:45. So your
So for what sort of light source you have this second order stationary?
So any realistic optical source that, say, let us say the field emitted by an incandescent bulb or a gas discharge tube can be modeled as a white sense stationary because to begin with, the timescales over which we make the observations are much longer than the timescales of statistical fluctuations. So which means the fluctuations average out by the time we make the measurement. So what it tells us is the mean is basically time independent. So that's one of the reasons why the optical field from any realistic source is modeled as a white sense stationary process. Because the intensity is basically doesn't fluctuate. You can turn on any light bulb, we don't see random fluctuations of the intensity. It's quite stable. So even though there is randomness, most of these sources do exhibit some sort of statistical stability. So that's why we are justified in modeling the optical fields produced by these sources as a white sense stationary process. And in this case, for a white sense stationary process, the autocorrelation will only depend on tau.
But then why even white? Like this light in this room can be modeled as first order stationary. Why the second order?
Oh no, because if you want to calculate the correlations at two different spatial points or at two different instants of time, you need to have a joint probability density, because here you just have one x and one t. That's why. So whenever we talk about correlations in optics, it's always correlations, how the field is correlated with itself at different instants of time or at different locations in space, or how are two different fields correlated at the same instant or at different instants.
First order stationary process is also, yeah, now I understand. Now first order stationary process is also second order stationary, but converse is not.
Yes, true. So basically in this case, so this is how we define the autocorrelation, and it has some properties. R of 0, which is basically so of course it's easy to convince ourselves. Let us assume that x of t is a real quantity. It's a real random process. So x square is a non-negative quantity. So the square of, so which means the average of a non-negative quantity has to be greater than or equal to 0. It cannot be negative. So that's what it is. And second significant property is R of minus tau. It will become mod.
That's Z and Z star. So actually,
yeah. So it's Z and Z star. So still at when there is no delay, this will still hold good, even if your optical signal is complex. And of course, the third significant property is so the maximum value of autocorrelation occurs at tau equals 0. Okay, that's the upper limit. So for any delay, whatever you calculate, whatever be the autocorrelation function, its absolute value will be less than or equal to what you calculate at R of 0. because the autocorrelation can be positive or negative. That's why this absolute value comes into the picture. If it is positive, it just means that the variation is in the same direction, or if it is negative, it just means that the correlations are in the opposite sense. Say when one at one instant when the random variable takes a positive value, the other one takes a negative value, or vice versa. So autocorrelation can be positive or negative. Okay, so this mod r of tau is always less than or equal to r of 0. So the maximum value that your autocorrelation can take is when tau is 0. Oh, the third one? That okay. So what you do is, okay, quickly, okay, let me just. So if you want to prove, this one, start with this one. Let us take some arbitrary instance of time, t1 and t2. Okay, this should always be greater than 0 because this is a positive quantity, right? Now, if you expand this, let us take t1 as t2 minus t1 is tau. So which means this becomes, right? So here it just, this is r of 0 because it's just a x square of t. t1 and t2 are arbitrary, correct? So you have
I cannot make both 0, right? If one t1 I am making 0, then
no. So your definition, r of tau by definition is x of t times x of t plus tau. So if tau is 0, it is just x square of t, correct? So here you just have x square of t1. t1 is arbitrary, so this is r of 0. Likewise, t2 is arbitrary, r of 0. So r of 0 plus or minus r of tau is greater than or equal to 0. So this plus or minus is what gives rise to that modulus.
not that much obvious.
This is a simple proof. This is how you prove it. So this is how it is. So we'll just stop here today because we have a seminar at 3:45. So next time we won't meet this Friday because it's a public holiday. The whole of next week we have this conference. So we'll meet on September 16th. So what we will do is we'll just briefly discuss the concept of ergodicity. An ergodic random process is one where the time average is equal to the ensemble average. So we'll discuss the concept of ergodicity, introduce the notion of complex analytic signal, and then we will see how all these ideas are used to calculate temporal coherence and spatial coherence, so on and so forth. Okay, and then we will try to do a full-fledged calculation of correlation functions in an interferometric setting, and from there we will branch off to quantum optics and see how correlation is defined in quantum optics, what are the various quantum states of light, bunching, anti-bunching, so on and so forth, and then get into interferometry with quantum states of light slowly. And later we will once again come back to a rigorous treatment of spontaneous parametric down conversion. And some of these ideas on coherence will once again manifest when we deal with entangled photons produced through spontaneous parametric down conversion.